Hi. Yes, I can't help myself. I keep buying test gear on eBay. This one popped up and it is repair. So it was sold as not working or not powering on. What is it? It's a Stanford Research SR650 dual channel elliptical filter designed for audio, low frequency. It's basically DC to 100 kilohertz. So basically that audio range plus low frequency vibration and shock analysis and stuff like that. Really handy ones. I've never had a programmable filter in my lab and I've always wanted one, but they've always been pretty expensive. There's a couple of companies that make them. Stanford Research is one, Rockland is another, and there's a few others on the market as well. So, you know, one of your more obscure bits of kit, but if you need one, you need one. One of those things. So anyway, I'm hoping this will break the EEVblog curse where the faulty products are either just so incredibly simple, like a blow-in input fuse or something, or they're just beyond economical repair, BER. So I hope it's somewhere in between there and we should be able to fix it. Now, the good thing about Stanford Research gear, you've seen some Stanford stuff on my blog before, is that you can get the schematics for them. The manuals come with the full schematics and everything else. I don't have the schematic for it. I haven't tried to see if I can download it somewhere, but you can at least buy them, which is great. The other thing is that Stanford Research gear looks like it's been designed in the early 1990s. It's all dip technology, or uses almost always off-the-shelf parts, so very repairable. I'd be surprised if this thing is beyond economical repair, unless it's the power supply has failed. They're usually linear power supplies inside these things, unless it's somehow failed and like taken out everything, and that might make it beyond economical repair. But anyway, yeah, we should be able to have a good shot at it. So I picked this up for just over $100 on eBay, and they still sell this. It is still a current model, but it was designed back in the 90s or something like that. And it goes for $3,300 new. So beauty. This is the 650, which is the dual channel version, which means you can do bandpass filtering as well, because you can select high and low frequency, and you can do that bandpass. So let's crack it open, see what we got. Sold as just doesn't power on or something like that. Let's have a look. So yeah, these bits of Stanford Research gear, these type of ones, what they usually are is just like a little 8-bit micro, and then basically all just passive stuff and switches and muxes and stuff like that. That's what'll be inside this filter. So, you know, really, even if, a power supply has failed and taken out a lot of stuff, probably still repairable, even if you had to replace, a whole bunch of op amps or something like that. Might still get lucky. So really, there's not much else inside this thing. And this, here we go, this company knows how to pack stuff. Look, there we go. They've got the molded foam, the Instapack it's called. So this is a proper professional test equipment company. It's the Outback Equipment company in Gilroy in California. So excellent, well done. So if you're going to buy stuff from them, well, I would, yeah, look at that. I mean, that is just fantastic. That's how you should pack test gear. That's brilliant. They've just molded these in here. They've chosen a box and then just molded those in specifically. They've got the machine, the Instapack machine, to manufacture just the right but yeah, basically you put these what you do is you put the plastic in there, and you've got a machine which then squirts the stuff in, and then it just molds around the shape of the product. So this is really good. So it should have come to me in good condition. It looks a little bit crusty. There's a bit of, I didn't get anything else with it, no manual or anything like that. There's a bit of rust on it. Yeah, it's not a new unit, that's for sure. And yeah, there's a bit of corrosion on the B&Cs there. That's, that's not terrific, but we can clean those up. But even if something like the B&Cs are ruined, you could always replace them in gear like this. So to scope, yeah, somebody's written on there. Yeah, thanks for that. Terrific. Yeah, lots of rust on the screws. So yeah, there we go. Quite a bit, pretty crusty, but hey, Let's crack it open. Well, no, I'll power it up first. Serial number 28078, and they probably would have made that many. So, yeah, it's not going to be serial number 78. It could be 8078, but I doubt it. Stanford have made a lot of these things. Made in the United States of America. Actually, there doesn't seem to be a voltage select in there. Like, I think I'll just crack the lid off first and see, make sure there's no jumper in there for 240 volt operation. So as I said, it'll be all dip, mostly all dip technology. I'm actually surprised, I'd be surprised if it's not 100% dip technology, probably on one or two big boards. There'll be a processor board and there'll be probably a big analog board. They might integrate them into one. I don't know. This is an 8-pole elliptical. Oh, yeah, mixture of screws. Somebody's had a go at this. Man, we had flathead on the other side, and then we got a Phillips, and then we got a tiny little hex. Unbelievable. So I'm a little bit concerned about the amount of rust on this. You got to wonder what sort of life it's had. And hey, ta-da! Look at that. That actually looks fairly clean. I don't mind the look of that at all. There we go. We've got two big analog boards because this is a dual channel unit. There is a lesser model in the 600 series that only has a single one, so you can combine the two channels. And so there we go. I was right. There's an entirely separate digital board up here, and yes, everything is through hole, and then a separate analog board for each channel. Look at that. I mean, that is hugely repairable. We've got all of the designators all there, nicely spaced out, all dip. We could just pull that board out and desolder things if we have to. Not socketed. None of the, the memory and stuff over here is socketed, and the ROM, but apart from that, yeah, that's pretty darn good. I'm happy with that. And of course, this is exactly what you see inside a filter. We've got a whole bunch of just passive components, and then just muxes and switching stuff like that. So that's pretty much all there is to it, because it's just an elliptical filter. It's just using op amps. So here's all your input op amps and stuff over here, and then the rest would be, and then you've got all the different range resistors and stuff like that. So yeah, I mean, so it shouldn't be hard to get this thing up and running, but well, let's power it up. Here's what I was afraid of though. Look at all the wiring going into that fuse holder over here, coming from the transformer taps, the primary side here. And I love the big clunk and mechanical switch coming from the front panel, of course. None of this soft power rubbish. I like it. So yeah, I don't see any initial labeling on there, so there could be a 240 volt configuration of this wiring. So before I power it up, I probably should consult the manual. Or actually, I can just do it the easy way. Oh, just got out my 110 volt transformer. So using one of those weird ass Yankee plugs. So let's power this thing on. So it came from the US, so presumably it's still set for 110. If it's set for 240, well, it's going to be under voltage, so not a problem. I've found that some dealers will actually know, if they're shipping it to Australia, will actually set it to 240 volts for you before they ship it. But anyway, let's go. Nope, he's right. Nothing. Dead. Wah. Well, first of all, before I measure the power supply, I'm just going to do a quick check of that backup battery in there. There we go, 2.92 volts, that's okay. So that is still hunky-dory, hasn't leaked at all, although in this sort of vintage gear, you'd probably replace that. What date code? We're looking at 9624. Yeah, 96 seems to be the latest that I can see. So yeah, that mid to late 90s vintage. It's got that mid to late 90s smell too. Alright, before I start poking around the power supply, let's make sure that the primary of our transformer is there. So my power switch is on, and we'll just measure that. Well, there's your problem. Look at that. No, can't measure the primary side of the transformer. So that fuse was good. I had a look at that before I powered it on, and yep, it looks intact and measures intact, so nothing wrong with the fuse. So the primary of the transformer, I'm wondering if maybe there was a, sometimes these transformers will have a thermal cutout in them, so maybe that could be an issue perhaps. But anyway, if we can solve the primary side of the transformer, maybe this thing will come to life and maybe there's nothing wrong with it. I mean, that's ideally what you want in these sort of repair scenarios. If there is actually electrically something wrong with it, then usually you're sort of hoping for a power supply fault, because they're the easiest things to fix. You know, if it's something like the EEPROM has died in it due to age or something like that, or there's something else, you know, some other fault or some other failed chip or something like that. But usually it's the power supplies that are going to fail first. So heck, we're not even getting into the primary side of the transformer. Goodness. Now here's something interesting. Check this out. Here is the mains input filter here. So they've got a nice little filter module in there with a common mode choke, and I'm measuring the output of that. And there we go. We've got our 35 ohms. So, hello, that has to be the primary of the transformer. Let's switch it off. Yep. The input pins on the IEC are supposed to just go straight through the filter and out to these two pins. So we measure our primary of our transformer here, but we don't measure it on these pins. That is strange. I don't think I've ever seen one of those filters die before. Unbelievable. And you can see the circuit there. I mean, it's just a standard input filter. They've got the common mode choke there and the suppression caps input and output going to ground, but that's it. Like, it's not like it has any internal fusing. So really, for that, one side of that common mode choke has to be broken in order for there to be no continuity between the pins, the input pins over here, and the output pins here. Whoa. So let's measure that. No, nothing. There we go. There we go. So we've got direct continuity on that pin there. Let's try the other pin. Should be this one. And of course, no. Often these things will be potted too. So, I don't know. Well, let's try. This one's not though. This one's not. So, well, might have to, it's probably welded shut, but we might have to rip that thing open and have a look. But I can sort of bypass it because I can just take off, I can, oh no, they're soldered on. I could desolder those and feed the mains directly into there to bypass it. But, jeez, I wouldn't have thought the mains input filter. Go figure. I just noticed something out of the ordinary. Look how all these chips are soldered in. Yet this one is socketed. Why? It's almost as if that board has been repaired. I mean, that's just a 74, what is it? 74HC04. Yeah. So that filter just popped out of there. These clips were just holding that in there. So yeah, there it is. See, it's soldered shut there. So we can get the iron on that and whip that sucker open. Maybe there's like some internal wiring that's just broken off or something. Maybe there's a board, maybe it's a right angle IEC connector or something, and yeah, just the internal wiring to that is broken perhaps. So I'm having some luck on this. It looks like this whole top cover here can slide off. Hey, nice. There we go. We're in. And check it out, this isn't exactly professional construction on your filter here. There's the common mode choke wrapped in electrical tape, and there's your mains rated caps tucked away in there. 3 of them. Oh, goodness. Okay, well that's embarrassing. I missed the voltage selection switch. I knew it must be in there somewhere with all this wiring going into there. It didn't make sense just to sort of terminate it in there and and solder them in the correct position. And yeah, it's tucked, it's slid all the way down in there, and people watching this probably, you know, were screaming at me all along, oh, there's the voltage selection switch. Yeah, I missed it. I'm watching the screen of the LCD here. So I miss these sorts of things. Anyway, yeah, it was in the 120 volt position, so I can just whack that around and slide it back into the 240 volt position. But that doesn't explain why our fuse is good and we're not getting from the output terminals of the filter through to the IEC, because of course the IEC input will be going through the fuse and then through to the filter side of it. So the fuse has to be in that path there somewhere, I think. Okay, now I'm fairly convinced I've figured out what's going on here. Here is one of the IEC, well, here's the IEC input connector here, and of course it's not connected through to there, and it should be, but it is connected through to the fuse there, and of course that goes through the fuse, and I can see a trace running onto the other side, and then that has to run back to this common mode choke over here. But there is no connection between those at all, that fuse and the other common mode choke. That's why we get no continuity from the IEC through to there, whereas the other one, the other IEC input pin is here, and we're getting continuity just fine. So I've actually resoldered, I've reflowed both of those and added new solder through, but because the connection is on the other side of the board, I can't physically get in there to check that, but I'm pretty sure that is supposed to connect through to there, and it doesn't. Grrr. Oh, and by the way, in the 240 volt position, we're getting, of course, double the primary resistance, 52 ohms, whereas we're getting 25 ohms in the other position. Actually, I'm beginning to think somebody's had a go at this. There's a nut missing out of here. There's only actually one nut holding the transformer on, and, well, I don't know, it kind of looks new, and check this out. Here's the secondary, and the secondary has this wire sort of, hanging out here like this. It's not like the others, and it hasn't been cable tied with the others. So I'm not, I'm not entirely convinced that somebody hasn't been fiddling with this thing. I don't know. I just get the warm fuzzies. That's the case. All right, so I put a mod wire in here, but I don't know, I'm getting the heebie-jeebies. There's a reason why that trace under there, and I'm pretty sure that's the trace, is broken. I tried to desolder the pins and lever it off, but it was just all too awkward. Couldn't get in there. It was a pain in the ass. That wasn't going to work at all. Okay, I've put a 1/2 amp fuse in there. I'll run it through my 3-phase power meter. I've disconnected the secondary from there just for now. I just want to power it up and get the primary. So let's give it a whirl. And 1.5 watts. There we go. That's not too bad at all. Okay, here we go. Moment of truth. We've plugged the secondary back in, and let's give it a whirl. See if anything powers up. Woohoo! Look! It's alive. It's alive. It's doing something. There you go. Nothing smoking, so we're at least getting, yeah, the micro and everything else, AC, DC coupling, overload, yeah, who knows, these are fed input things, I believe, often, no, there we go, it's just resetting, there we go, so, hey, the micro's working, everything's hunky-dory, so something blew the ass out, well, or there's an intermittent track in that mains input filter there. Huh. Go figure. One thing I'm definitely going to do is replace that crusty, noisy fan with a modern silent one. Definitely do that mod. Now, one of the good things about this amp is that it's got differential inputs too. Here it is. It's you can either select source A or source B as single-ended, so you can actually use it as a switch to switch between two input signals, or A minus B is, of course, the difference, so you get a differential input. And, of course, we've got those on both channels, so two totally independent channels, as we saw, two totally independent boards on there. They'd have their own isolated power supplies, everything, so fantastic. And then you've got your input gain, of course, for each one, so you can gain it from anywhere from 0 to 60 dB. Very nice. And your output gain as well. So beautiful. All that's left to do is feed a signal in and see if it filters, because that's all it does. It's a filter. Alright, to test this, I've got my DSA, my Dynamic Signal Analyzer. Why? Well, because I can, and I love dynamic signal analyzers. You don't need a DSA to test something like this, of course. All you need is a function gen, a sine source, and your multimeter or your scope, and you can sweep it over the frequency range and determine it. But anyway, the DSA will allow us to sweep the frequency up to 100 kilohertz, which coincidentally is the limit of this thing. So fantastic. What I'm doing is the source output here, I'm generating 1 volt RMS of random noise. So there it is, 1 volt RMS there, and the reason I'm doing random sources is because this doesn't have a swept sine generator. So what we can do is we can generate random noise. So it generates random noise over the entire spectrum, and then over time you can average that out and get a flat spectrum response. So let's actually start that. I've turned averaging on. I've got 100 averages there. What I'll do first is I'll actually show you that noisy input signal. Now it's working like a scope now, so there's our input signal there. It's just garbage, okay? So we can turn that source off, of course, and bang, it drops away to nothing. So there's our 1 volt RMS random noise, and random noise is actually very useful, especially if it's proper random noise, so then you can actually average it out over, because the power in each frequency bin over time is going to be the same, so you can average that out. So anyway, let's turn that back to our spectrum, and then let's start. Here we go, and you see how it starts out noisy, but then it eventually gets flat. So I'm just feeding the source directly to the channel 1 input, okay? So it's flat over the entire frequency range. Now, what we'll do is we'll put our filter, our Stanford Research filter, in series with that, and we'll set it to 50 kilohertz smack in the middle, and we should see it go flat and then drop off like a brick, almost like a brick wall, because this is an 8th order filter, really high order filter, so it should have a really sharp fall off right at 50 kilohertz, pretty much smack in the middle there. Alright, we're in the low pass side of it. The other side is an identical channel, but it's a high pass filter. So it's automatically defaulted to 5 kilohertz at the moment. Well, let's just ramp that up. You notice how it just shows up enter, like don't believe it changes like dynamically as you go. You've got to hit enter before it actually applies it. So that's why it's warning you there with the big enter thing. So the dynamic speed there isn't bad. There we go. Spot on 50 kilohertz. We'll enter that in. So that's our low pass filter. Our input gain 0 dB, our output gain 0. So we should be hunky-dory. So let's just go back to here and run this again. And where cursor's at 51.2 kilohertz at the moment. So just before that cursor, we should see that drop off if this sucker works. So let's press start again. Hello, look at that. There we go. It's not exactly a brick wall. It's dropping off, but there we go. It works. What if we lower the frequency down to say 10 kilohertz and see what happens? There we go. I won't bother zooming in on the DSA. There we go. Let's run that again, and we should see it drop off about here. Calibration. Come on, give me a break. Come on. You can do it. Come on. Here we go. Average in progress. There we go. It's dropping off. Ta-da! Like the proverbial brick wall. This thing, as a first order approximation, pun intended, works. I'm very happy. That is a winner. Awesome. Well, at least the low pass filter stage. Let's try the high pass filter. So what we'll do is we'll just move this over here. These B and C's are a bit crusty. And, ooh, overload. That's not good. So, that doesn't sound good. 50. Nice round number. Okay, no, don't like the look of that overload. Okay. So, well, let's run it. No, not getting a good vibe there. And, of course, we should see a flat line here and then drop like that. But no, we got nothing. This thing, no. So, we could have a fault in, unless it's a PEBCAC and I'm using this wrong, because I haven't used one of these in donkey's years, absolutely donkey's years, and I haven't read the manual, of course. So no, those overload indicators aren't good, and you can whack the filter in and out too. It can just bypass it. That's very handy, but no, I don't like the look of that at all. Input A. No. We could have a loser on that channel. Woohoo! Excellent. More stuff to troubleshoot. But this channel over here, the low pass one, looks like it works a treat. Beauty. Now I'm back on the low pass filter again, and curiously, I've selected the filter out. So I've pressed the filter out button, and well, as you can see, the filter is still in. So, I don't know, there could be an issue there, but no big drama. And of course, the reason we're seeing a relatively gentle roll-off here is because we're in linear axes mode. So, go to your more traditional log axes, and you'll see it drop off much faster. There we go, it's got like 80 dB stop band attenuation, and if we wanted to, we could try and measure all that sort of stuff, but I'm not going to do that today. I'm quite happy that at least this low pass filter section seems to be working. Awesome. There we go, I auto-scaled that, and we can start to see the roll-off performance. Switched it down to 10 kilohertz here, so that's 100 kilohertz, that's 10 kilohertz because it's a decade, because we're a log scale, and 10 kilohertz, this would be 1 kilohertz. So I could drop that down to 1 kilohertz, just for entertainment, and, well, just overshot there. I've got to get it spot on. Here we go. Start. Boom, and we'll start to see it drop off at that 1 kilohertz mark. Beautiful. No, wait, hang on. I just tried that high pass channel again. I just repowered it, and the overload LEDs have gone off, and I set it to 10 kilohertz, and it's bang on. So I'm not sure what the hell was happening before, but that works. 10 kilohertz, high pass, no worries whatsoever. Wow, this thing's fully working. Okay, well, fully working. Haven't done complete tests on it yet, but hey, I'm happy with that. And what I've done here is put it in bandpass configuration. So my source is coming into here. We've set a high pass filter frequency of 10 kilohertz, so anything above 10 kilohertz it's going to allow, and then the output of that goes over to the input of the low pass filter, and then the low pass filter is set to 20 kilohertz, so anything below 20 kilohertz is going to be let through. So bingo, we've now got a bandpass between 10 kilohertz and 20 kilohertz, and the output comes from here back over, and look at that. Woohoo! There is our bandpass filter characteristic, 10 kilohertz to 20 kilohertz. Bang on. No, I just switched this to AC coupling mode and just permanently set it into overload. Not sure how to reset the overload on this thing. Might have to read the manual. But curiously, switching from AC to DC coupling, as you'd expect, I heard a relay. But this channel over here, the low pass filter, there's no relay. I don't hear it. And same with filter in and out. I would have expected that possibly to be a relay bypass, but I can't hear it. So anyway, there you go. That's a repair, in quote marks, of a Stanford Research SR650 dual channel filter, and it's a very nice instrument. If you can pick up one of these like I did for just over $100 and looks like it was just the mains input blown, then really there's not much else that can go wrong with this. I believe this uses the FET input just like the preamp. Stanford Research have a preamplifier, and it's notorious, the front end on that, for blowing the input FETs, but you can get replacement FETs for those, and actually repair one of those pretty easy. I can't remember the model number of that offhand, but the SR650 I believe uses that basically the same front end on that, so it could be a similar story with the FET inputs, but it seems to be working an absolute treat. So anyway, I'm going to repair the I can't put the cover back on the mains filter up there with that bodge wire on it. Doesn't sort of work. Maybe I'll sort of replace that noisy, horrible fan in there. Got to clean up the B and C's on these things, and yeah, just generally do some more testing on it. But hey, that's a winner. That's bandpass. There we go. That's exactly what I wanted. So now I've got myself a really powerful dual channel programmable filter. A very handy addition for the lab. And if you need something like this, you need it. They're great to have lying around. You don't use them all the time, but valuable bit of kit for your lab if you can pick one up like I did. Very nice. All right, I was hoping for something a bit more, you know, an electronic type repair, but hey, it's a mains track. Whatever. Catch you next time.